Handshakes or bows workshop.
Well, when you meet somebody for the first time, you greet them, and that's what this session is all about. And Cynthia is here as well, and she is going to be the person who will be manning the chat line, and she's going to answer some of your questions, and she's going to pass on some of your questions and your answers to us. So thank you, Cynthia. Caroline, you can introduce yourself.
Hello, everybody. As you can see, I'm quite colourful when I do my performances. I also do workshops, and Tony and I both have a very strong heart for reaching all those young learners in the world. We've got the handshakes, which is a great place to start. It's very mathematical. So the first hour is we're going to deal with primary and preschool maths, and the second hour is secondary maths.
Well, the subject today is handshakes, bows, and roses. Well, a handshake is a one-to-one greeting, and so instead of handshakes, we could be talking about bows, as long as it's a one-to-one greeting. And roses, well, that comes into it a bit later, and we'll leave that. It's an interesting way to think about the problem. So the problem is, for a group, everyone in the group must greet everyone else and say hello. And we want to know how many greetings that will be altogether.
We would plan handshakes, but you can't shake hands now because of COVID. So instead, people greet each other in different ways, with a bow or a nod of the head and a smile. But in Japan, the bow is the normal greeting. And so we're going to be talking not just about handshakes and roses, but handshakes, bows, and roses. And so, Caroline, you asked about the do, talk, record.
The technique we're using that's really powerful, it was disseminated by John Mason, I'm going to give him credit for it because he's amazing, is do, talk, record. So it's not about standing in front of your class, writing something down or getting them to repeat it and copy it. We first of all give them something to do. You can introduce it like we've just done. We've talked about the handshakes, but then get them to do it. And we're going to model that throughout. Then get them to talk about it in small groups or in pairs, and then share it with the whole class, and then recording it. So that's building, especially the recording is building a good discipline, even from the early years, even if they just draw a picture. So we're going to use that technique, do, talk, record throughout. There will be, we're giving you instructions. The instructions for you in terms of how to facilitate the lesson are in black. Then Tony's amazing at providing key questions. These key questions are questions you can ask the learners as they're doing the activity, as they're talking. You walk around and listen to what they're saying. As they're recording, you can ask key questions that can help guide them to think for themselves and come to their own realizations and their understanding for themselves rather than explaining. You're facilitating their understanding. And then in blue on these slides will be what we will all do, what you will do today. So those are the activities, the doing that you will do today.
Now, we're going to start with preschool. This is 4-year-olds, 5-year-olds, maybe even 3-year-olds. So what we'll have throughout this 2 hours is a theme, and even children as young as 3 and 4 can be introduced to these ideas. Get the children to talk about greeting, handshakes, touching elbows, hugging, bowing. And they can practice the Japanese bow. Don't bother about the angles, just practice the bowing. And encourage them to discuss the difference between saying hello to one person at a time and saying hello to everyone, whether they do it verbally or with a greeting like a handshake. And introduce the idea of everyone in the room greeting everyone else. And ask the question, how would we find out how many greetings that would be? And try this out. And the children can try it out with some soft toys, and they can play or enact the scene. First using 2 soft toys. How many greetings would that be? And then 3 and then 4. And only continue this sort of thing as long as the children are enjoying it. Don't make it a sort of, oh, you've got to listen, this is what we've got to do, all serious, but perhaps come back to the same game on another occasion. So for these preschool children, there's the do, which is the bowing, there's the talking about what they're doing, and there's the recording, which could be drawing a picture. And of course, as well as the bowing, there's having their toys do it and playing with the idea.
Once you've established the game, you can literally say, let's play the bowing game. And you can go back to it, or the handshake game, and just go back to it again and again. And each time you can ask more key questions, which are in the resource guide on the Aiming High website. Another really valuable thing in all of the resources is we're telling you what the learning objectives. We've got the theme. The theme today is number and shape patterns. Well, obviously number is important in your maths classroom. Shape patterns and number patterns are, number and shape are important, and number patterns and shape patterns are really important mathematical concepts. So especially start them early and keep them going with it. You will find that seasoned mathematicians' eyes light up whenever you talk about number and shape patterns. So the learning objectives, so the curriculum linked ones are counting this is the early years, applying the maths by counting, applying it to ordinary life. So the greetings are ordinary life, and the counting is what it's applying the maths to. And then the generic competencies, these are life skills. These are things that they're going to learn by doing these activities. These are the skills that they're going to learn that will help them in life. So connecting actions and ideas, making those connections, that's really important. And then developing communication skills. We all need communication skills. So these are the highlights of those from this activity for the early years.
We're moving on from early years to lower primary. And this is roughly 5 years old to 8, but don't worry if it doesn't quite match in your school. Every country has a different school system with different age groups, and they call the year groups different names. So this is very roughly ages 5 to 8, what's going to come up now. And all along we'll be saying to you, we're just making suggestions. You know your children, your class that you teach. You just pick and choose and reject and take on what seems right to you for the lesson you're going to teach. So this is now lower primary. Now, this is rather like what we were talking about. You should recognize most of what's on this slide. It's rather like the early years. There's no sort of sudden change once they start what the little children call big school. Here, it's talking about the greetings, trying the sakiri, which is the bow you see there. And now we might talk about different angles and how low we bow. And, you know, whether we bow right down so that our head is sort of level with our waist, sort of right angle, that sort of thing. And now we ask the question, how will you find out the number of greetings if everybody in the room greets everyone else? It's important that as with every maths problem that we face, it's important that everyone understands the meaning of it. What are we trying to do? And this is that we're counting all the one-to-one greetings, that is looking directly at one person and bowing to them, if it's bowing or shaking their hand. Now, here, you see in blue, we're going to ask you to do something in a few minutes and then write it on the chat line, and Cynthia will be seeing what you've done because you're going to tell her on the chat line. So we're going to see the next slide first, and then we're going to try this out as people maths. First with 2 people, then 3, then 4, then 5. Now you see in that picture there where there are 6 Japanese men, and they seem to be bowing in sort of one-to-one, but the people in pairs are bowing to each other. So it's not just 3 bows for 6 of them, it's a lot more than that. And so what we would like you to do is to try this out. And when I talk about people maths, I mean, it's actually get up and do something active, and you're actually doing the maths. But let's look at this slide first. We've got something else for you to do, and you should have a pencil and paper handy. I hope you never attend any sort of session without a pencil and paper. And you join each dot, draw your circles with the dots around them, and join all the dots on the same circle to all the other dots on that circle. Not between the circles, but on each circle. And you talk about what the patterns you see. If you're with a group, talk about the patterns you see. You could color in the patterns and discuss the patterns that people have colored and why they've done the coloring in a particular way. If they've colored it to show the patterns, then why did they color it like that? We thought you should do the people maths if you've got a group, but if you're on your own or there's only 2 or 3 of you, then you can join the dots. Just draw your circles and join the dots. But I think we can talk about these learning objectives. Now we're talking about the lower primary learners, and here again, it's a little bit similar to the early years, but here we're going to be asking them to describe the relationships or rules for the patterns. We're going to be asking them to describe them in their own words. We're going to ask them to describe the logical connections between their actions and the ideas. Ask them to, how do the actions of actually bowing to everybody, how do they link up with what you're trying to do, which is to solve a problem, find out how many there will be, and if you like, also, how does that link up with what we've been doing on joining the points on the circles? Now we're moving up to the 8 to 11-year-olds.
To apply the content according to your learners, you might need to go lower, you might need to go to an activity. Sometimes you can just start at the bottom and work your way up with any age, if it's a topic that they're not that familiar with or comfortable with.
Okay, so now we're going to think about this problem. And this was a classroom. There's me with a class in Tanzania, at a place called Bagamoyo, or just outside in a village. And you see this classroom, there's no glass in the windows, the bare brick walls, a very eager, lovely, lovely class, all very eager. I was saying to them, I wonder if we all shook, everybody in this room shook everybody else's hand, how many handshakes that would be. And they had decided how many there would be. If there were only 2 people in the room, or if there were 3, there would be 3 handshakes. And now there was 4 girls at the front are actually doing it. This is people maths. They're actually doing it. And everybody in the class is watching, counting. How many handshakes is this going to be with 4 people? And what was lovely about this school was we've got Muslims and Christians all together, boys and girls, a lovely, happy learning environment. I really enjoyed working with the children. I mostly work with teachers, but it's a joy when I can actually be with a class. And you see there the results on the board that we're writing down. We're making a table, number of people, and for each, however many people, the number of handshakes, we're writing those down. And
so it's over to you again. You're going to do this activity. So we're using the do, talk, record, and we're doing it, and you're doing it. So you're going to get practice in doing this yourself, so then you can deliver this with your young learners. Now, we had on there 2, 3, and then they were looking at 4. They'd written the results on the board. We're now going to have a go at 5. So we've already had a go at 1 circle with 5. Now we're going to see all the paths. So 5 children all greet each other 1-to-1. So if they both bow, that's a greeting. If they both shake hands, that's 1 greeting. How many greetings is if everyone greets everyone? So Mary greets Mzu, greets Nadja, greets Bob, greets Noko, Noko greets all of the other 4. Bob greets all of them, have to greet all of them.
It's a good thing to actually do this with the greetings, not with the circle. But the reason we put the circle is because you could do it either way, and because using the circle actually that does is to give the people who are on their own, because there are some teachers who are on their own, or maybe there's only 2 teachers, they can use the circle because there's nobody there for them to greet. Well, then they can use the circle. But if
you've got learners, once you're working, taking this and doing it with your learners, if you have 5 learners, or if you have 4 learners and you're one of them, then you participate, but you don't, all you're going to do is ask key questions and allow the learners to actually make the connections. And afterwards, once they've done the investigation physically, we call it people maths, actually do it by going around and bowing or shaking hands, then that's when you do the recording.
We have a response. Thank you. This is from a very brave lady called Antoinette, and one from Faith as well. So thank you very much. Faith can see, she's in Kenya at the moment, she can see 8 triangles. And Antoinette says there's some number patterns that's coming up. She hasn't described the number patterns, but she's at least seeing that there are different numbers happening. Oh, this is this is a school from the Eastern Cape. They've written the number pattern as 4 + 3 + 2 + 1. And Gary doesn't say where he's from. Gary says there's 10, 4, 3, 2, 1, 0. So we're seeing number patterns, we're seeing triangles.
And Antoinette, okay, virtual hugs, Antoinette, from one Antoinette to another Antoinette. That's actually my name, but everybody calls me Tony. So that's lovely.
She says she's from South Africa, and so is Gary. Gary is also from Uitenhage in the Eastern Cape.
Well, what you're going to find out is that as we go on, we're going to keep coming back to things. You might start your lesson and ask the question about 5 children all greeting each other. But as with problem solving, if you can't count the 5 right away, you might first of all count for 2 children greeting each other, then 3, then 4, and work your way up to 5 in this fashion. Now we're going to consider something slightly different. Okay, people maths, handshakes or bows. How many handshakes would there be with 8 people? Now, what you can do here is stand in a circle and suppose each chord represents 1 handshake. And you can do this with a ball of string like you see in the photograph there. You can try this and count all the chords. Take you quite a long time with your ball of string, so we're not going to ask you to do it with the string today, but this is like joining the dots on the piece of paper, and you see the 8 people around the circle there, and you could do it with string. And what you would talk about was how many handshakes there were and why that was the right number, and whether you'd actually counted them all or whether you'd missed any. And oh, there's a lot of people maths in that, and it's something that your class, if you want to do it with other teachers after this is over, then that's a great thing to do. You might want to share this with the other teachers in your school, but certainly we're suggesting that the children will enjoy doing this.
This is really, really simple. Everybody type in the comments what you can see. There's no trick question, there is no right, there is no wrong, there's absolutely no mistakes with this. You just type what you can see. So describe it and then think about how you would draw it. What do you actually need to be able to draw this? And then a nice question. This is where you start to evolve the maths and actually start including maths in there. Is how many points on the circumference of the circle. So, and now this one is the same again. Describe it. What can you see? it's
But it's a different pattern, isn't it, Caroline?
Yeah, is it the same or is it different to the last one? We're going to ask that question in a moment, but again, describe the design. How is it made? How would you draw it? Now we've got them side by side.
Yep, we have a response from Mike. He's just written, I can see a circle in the middle.
So one has a circle in the middle. What about the other one? And why has one got a circle and one doesn't? These are all questions that lead from the art, as it were, into the maths. It's like, okay, now we've got to work out why. And how many points are there on the circumference of each shape?
He's just making the point which I was trying to make, but I think Caroline didn't quite see. They both have circles. He can see a circle with lines going through the circle. So I mean, what he's saying is you can't say one's got a circle and the other hasn't. Mike says there's something different about the circles, but he can still see two circles.
Yes, and whatever you say, we want you to explain why it's happening. And also, I would like to ask another awkward question. Is it really a circle or is it really a polygon that you see?
And if it is a polygon, how many edges has it got? Although the one on the right is a little bit of a trick, because the one on the right, there actually is a circle there, just so that you know. There's a circle. There's a circle outside of the shape. Yeah, it's maybe to demonstrate that there is points on a circle.
We have points. Someone has told us how many. Do you want to know?
Yes.
Yes. So this is Gary again, and Antoinette. So we've got two respondents. Gary says there are 15 points on the first circle and 16 points on the second circle. And Antoinette says the center circle is formed by opposite points and the tangents to the inner circle from the same point to the opposite point, adjacent points. I've probably not read that very, very accurately, but she's talking about points and tangents to circles and circles being made by tangents.
Yes, and that's excellent. And I'm going to ask another question, and that is, well, it was 15.
Yeah, sorry, Tony, we're interrupting again. This is a lovely question from Mike. I like it. Is a circle a polygon?
Well,
that's an excellent question.
Now here, especially for those of you who are teaching in upper secondary, we'll be thinking about limits. So here we've got, a circle is the limit of a polygon if n is the number of edges of the polygon and n gets bigger and bigger and tends to infinity, then the polygon tends to a circle. So in the limit, it is a circle in the limit, but actually a circle's different from a polygon. A polygon has to have straight edges, even if there are millions of them, and you can't tell the difference when you look at the picture. That's all very technical, isn't it?
One of the things I do especially when a young learner that you can't talk about tending to infinity and at the limit if they're too young for that, and even if they are old enough to understand that, when they can see, well, that's not possible, I always say, you'll be a great engineer. That's the difference between an engineer and a mathematician. An engineer stops at reality. Think, well, that's not possible. Okay, that's a really good point. And that's the beauty of mathematics, that you can go to places that are impossible using your imagination.
And Caroline's an engineer, and, well, I'm a maths educator. So now we're going to come on to key questions. Now, what you see on the left there is a worksheet. So we're going to imagine that you've given this worksheet out to the class, and the do, talk and record for the class is completing this worksheet. What they're doing is joining the dots, as you did earlier. They are comparing the patterns, looking for patterns, and they're looking at what's the same and what's different. So while the children are working, you as the teacher, now you shouldn't have taken you many words to give them that worksheet to do, because basically you want to try at the beginning of the lesson as a teacher to say as little as possible. And so it's the children who are doing the talking, not you, and it's the children who are doing the doing. Now, what should you be doing? You should be guiding their learning. That's the role of the teacher. And you do that by asking questions. And here in green, we've got some examples. So as you see what the children are doing, you then talk to them, either to the little group of children or to them individually. And you say to perhaps one of the children, suppose you only have 3 points on a circle and every point is joined to every other point, then how many lines would there be? And then what about the number of lines for 4 points or 5 points or 6 points? So you see, you're prompting them, not by telling them that they should do it, but asking them questions which will then prompt them to go on and do, you're guiding their learning, going on to do something which will help them to learn. And the reason we're making these green text here is because green is like new shoots of learning, new growth in learning. So you think of key questions that way. And then you might ask, how many points are there around that circle, pointing to the one that the children are actually doing at that moment? And then you might ask a question to another group or another individual learner, can you count the number of straight lines and in that diagram? You might ask them, do you know what those lines are called? And you might introduce this little extra bit of language, the word of chord, and you will know whether your class should have learnt that word. And then this is for the children who are galloping through this and getting, getting some answers. You say, this is the ones who are the high flyers. You can say to them, if you had 100 points, you wouldn't want to count the lines, but could you work out how many lines there should be? Now, you wouldn't necessarily ask that to the whole class, because some children are still trying to work out how many there will be with 6 points or 6 people. So, and some of them have, only done 3 or 4 of these circles, but you may see somebody has done all the circles on the worksheet, and then this is like what we call differentiation. This is for the high flyers, this last question here. Okay, so that's doing the worksheet.
In the activities on the Aiming High website, every single one has key questions. So anything you want to use, and that's all free to use, all you have to do is download it. You can use, there's an app for your phone, and every single one has key questions to help you facilitate, help you guide the learning. This one is recording again. So this is how to record what we were seeing with the circles. So you've just done the activity with the circles. Now we're going to record it. We've recorded it, let's say, we've explored it using the circles and the lines. Now we're actually recording it to see the number patterns, to really see the number patterns clearly, being systematic and very clear here. So you again ask the questions that go with it. Tony's just filled in the blanks, and then as they go up, then what is going to be, how many chords are or greetings are they going to be if you have people doing it? And then this is another way of recording it. So if you see those numbers, you can actually record them all in the form of a triangle. So this is a way to introduce triangle numbers if you haven't introduced them before, or if they already know about triangle numbers, it's a great way for them to recognize another system, because triangle numbers come up again and again and again.
So really what we're looking at is trying to recognize patterns. And one thing that children may do is to realize that when they move on from 2 people to 3, there's 2 extra handshakes. And when they move on from 3 to 4, there's 3 extra handshakes. And then there's 4 extra, 5 extra, 6 extra, 7 extra. And so children might tell you that. So you keep asking them to explain, what patterns do you see? Can you explain that pattern? And so they may not know the word triangle number. They may have not seen these pictures before, but it's now beginning to come through for some of the class, at least, that what we're adding up for, say, 7 handshakes would be 1 plus 2. Now this is working through the picture from the top to the bottom. 1 plus 2 plus 3 plus 4 plus 5 plus 6, and that gives you 21 if you count them. But we'll come back to that. So don't worry if it's not clear to you now. We're going to come back to it. But this is the point, really, that you just feel your way through, you understand as much as you can, and you try and explain what you see, because by putting the ideas in your mind into words, it helps you to sort those out. And so
and we've had two answers who said that the last line is 36. So Cynthia has gone straight in and said, so what about 20 people? So if anybody has come up with the answer there, what about 20 people?
yes,
they're not allowed to stop and do nothing, are they?
no. Now I'm thinking about sort of oldest children in a primary, but well, in a European primary school, the oldest children would be likely to be 11 years old. Typically, I'd say that I've worked on this problem with children of this age group, and in a class, some children will actually be using method 1 and some using method 2, which I'll talk about in a minute. That's what the boxes are for. But if your class finds the patterns and talks about the patterns, but doesn't get any answers, or doesn't get the general answer for 100 or for a bigger number than that, rather than tell them the answer and explain it to them, leave the investigation unfinished and come back to it at a later time. So what we're doing in this workshop is talking about a spiral curriculum. You'll see that as we started with early years, and year by year, we're coming back to similar ideas. And the idea of number patterns comes up again and again and again. And you don't push too much at any one stage. You just help the children to make some progress. And next year, you'll come back to the same sort of, other ideas about number patterns. So what did I mean by method 1? Well, method 1 is where you're thinking along these lines. If you've got 20 people and they each greet how many other people? They each greet 19 others. And that must give you 20 times 19, which is 380 greetings. And quite a lot of children will come up with that answer and be quite happy with it. But then you have to ask the question, so if I greet you and you greet me, how many greetings is that altogether? And so the penny will then begin to drop. Oh, it's the same greeting. We've greeted each other. So maybe we have to divide by 2 and we get the answer 190. Okay? Now in a typical class of 11-year-olds, some of the children will be a long way from finding that out for themselves, and other children will actually discover it. And I think it's fine to get the children who've discovered it to explain to the other children. But what I'm saying, I think, is, as in the bottom in red here, if nobody in the class can do it, leave it for another time. So now what about method 2? Now this is quite different, okay? So so this is another method that people think about. If you're the second person to go into the room, then how many greetings is that? Well, there's only you and the person in the room and the second person to come in, there's only 1 greeting. Now, when the third person comes in, there's 2 people in the room, the third person greets them both, and that adds another 2 greetings. And then the fourth person comes in, and now when that fourth person comes in, there's 3 people in the room, the fourth person greets those 3 people, and so that adds another 3 greetings. And the 5th person comes in, there's 4 people in the room, so that adds another 4 greetings, and so on. And this leads you to the idea that if there's 20 people, you add up 1 plus 2 plus 3 plus 4 plus 5 and so on up to add 19. And if you add them, those numbers, you get 190. Now, whatever it is you're doing in class, it's likely that the way that some children will think of doing it, it might be just multiplying 2 big numbers together, whatever it is, that some children will think of doing it one way and other children will think of doing it a different way, and neither of them might be the way you thought of doing it as a teacher. So typically, in many classrooms, many teachers, and this might have been your own experience when you were at school, the teacher will have said at the beginning, this is how you do it, would have shown you the method, written the method on the board, and then given you some other similar things to do, but you do it exactly as you've been shown how to do it. And then that sort of teacher will expect everybody to do it using my method. I'm the teacher, I'm going to tell you how to do it, okay? And the kindest possible way a teacher might be doing that. But actually, that's not a good way to teach. What we're trying to say to you is, be aware that there are lots of different possible methods. Be aware, and you will see them on the Aiming High website when you look at these PDFs, these things, these documents you can download. There will be more than one method. We give you the solutions, we give you the different methods. Look out for what the children are doing. They may not have thought the whole thing through, but there's nothing wrong with what they're doing. So to tell them to don't do it that way, do it this way, isn't a good way of teaching. Okay, so typically with this particular problem, they may not get to the final answer, but there's these two approaches and they're both equally good.
For this one session that we're doing with you, there are 3 really powerful activities on the Aiming High website, all with key questions, all with teacher notes.
We're going to talk about the learning objectives, which are about the maths that they're going to, the hope that they're going to learn. Now, not every learner will be able to do each one of these as you see them and actually get there, reach that objective, but different children will make different progress, and this is what they're having the opportunity to do, and this is what you're helping them to do as a teacher. And then the generic competencies, these are the skills for life that are not specifically mathematical. We're going to talk now about the full age range, 11 to 16, and then later on we'll talk about what we're calling college maths, which is for 16 plus. The Do Talk record sums up in just 3 little words a whole lesson. In fact, many whole lessons, perhaps every lesson. It's what the children are doing, and what is the teacher doing? The teacher's guiding the learning. The teacher is asking these key questions which open up the learning. That's why we call them key questions. And it's green because these are the green shoots of new learning that are growing while the teacher's guiding and nurturing and fostering this learning. What we're talking about now is starting a lesson. We've got a secondary school class, and now we're starting the lesson. How would we start it? Well, we'd first of all make them aware that this was what it was all about, and then we would introduce the topic. And there you see me in a classroom in Tanzania, introducing this idea, this problem, which they're all trying to solve. And you see in the lower slide, there's 4 girls out there in the front, and what they're trying to do is to work out how many handshakes there would be if there's 4 of them, if everybody there, each of those girls, shook hands with everybody else. And this is like a football league where every team plays every other team once. So it's handshakes, but in a football team, it's football matches. But the point is that everybody has this interaction with everybody else in the football league, if it's a football matches, or in this case, the greetings. And the key question is, how would you find the number of greetings? And the learners should talk about the problem in groups. They should see if they can think of any ideas about how to work out the number of greetings for 6 people without actually counting them. And the groups that can find it out for 6 people, then they should try and find the answer for 20 Okay. And so what we want you to do is to see the next two slides and try this out as people maths. Actually, if there's a group there, you could do the handshakes, or if you can't, obviously you could do the bowing instead of handshakes. And then the next slide, now you've seen this before if you've been with us or through from the start. But now, if you have done it before, then color your patterns. What does your coloring show? Okay, there's something about these patterns. If you join the dots, this is for two people on meeting each other, or 2 dots on a circle, then the next one is 3 dots, 4 dots, 5 dots. Then color the patterns. What does that show? The position of the secondary school pupil for whom this lesson has now been running about 10 minutes. And you're now trying to use these circles to work out how many greetings for 2 people, 3 people, 4 people, and 5 people. And we're now looking at geometrical patterns in the coloring that you might do. Okay. And that might be a rotational symmetry or something like that you would see in the pattern. And as if you think of this as art, and there's a lot of people in Africa, the African art, beautiful designs in African art, and the coloring actually is showing up the symmetries in the design very often.
The first circle, you have a line segment. Are we assuming this is symmetrical? Tony's asked us to look at symmetry. So are we assuming that these dots are absolutely evenly spaced around?
No, they could be, couldn't they? I mean,
if you were asking for symmetry, weren't you? In which case, what is that segment called? That's another question. We had some more comments, Tony.
Yes.
From the Eastern Cape, they're expanding on what Caroline just shows. They say that with 4 points, you get a quadrilateral, but with its diagonals included.
Before you go on to 5, now I want you to close your eyes and imagine something, everybody, okay? Imagine this, okay? Caroline's got her eyes closed. I think Cynthia has, okay? Now then, imagine not a plane, 2 dimensions, imagine 3 dimensions. And imagine your 4 points and 6 lines so that every point is joined to every other point. What solid have you got now? You've got only 4 points.
Oh.
But they're in 3-dimensional space. Every point is joined to every other point. Okay, so you've got 6 lines, 6 edges of your solid, and 4 points, which is 4 vertices of your solid. What solid are you imagining?
Brilliant. That took me a minute to dawn, but yes, it's lovely.
You would only get a square if you made them go, if you push them all 4 vertices onto a plane, onto a flat surface. Yeah. I'm sure every school syllabus requires you to look at properties of 2D shapes and properties of 3D shapes. And that's what we've been doing.
4 vertices, 6 edges, make 1. And see what shape comes out, and then see how you can relate it to that shape in the circle.
Now, while the learners are doing what we've just been talking about, and then you're going to be, as the teacher, asking these key questions to guide the learning. And one of those questions is the 4th one down. It says, this is a question you can ask again and again and again. Can you explain how you found your answer? That's probably the question as a teacher you should ask most often. So you ask a question, a learner gives you an answer, and the thing you should be saying often is, can you explain how you found your answer? And it should be so habitual that you never let anybody get away with giving you an answer like 27 or it's a cube or something. You always ask, Can you explain how you found your answer? Now, the reason for doing this is that it's really useful for the learner who's actually doing the explaining. They're developing communication skills and actually thinking mathematically while they're doing the explaining, but it's also helping the rest of the class, because it's no good a few children can answer the question and the rest cannot answer it because they don't know I don't know how to find the answer. But having Mizzou explain to the rest of the class, or Najwa explain to the rest of the class how they found the answer, will help the other children. So that should be the question you ask more often than anything else. And it's a question that always applies whatever the work they were doing, whatever sort of work the children have been doing.
What we've got is the same thing, and this applies just as much to secondary as it does to primary. So it's about what you see. It's about describe the design. It's about thinking about how to draw it and looking at the points on the circumference. You're starting to hopefully see, looking from what we've just been doing, how valuable that is.
Now, the reason why we're repeating this is that what you see in these few slides in sequence here is a complete lesson for 11 to 16-year-olds. And of course, we're doing some of the same things as we did for the 8 to 11-year-olds.
Spot the differences and how many points are there on the circumference of each one, and why are they different? Are they circles? Imagination could be used with these to just have a vibrant maths discussion.
What we're trying to help you with is to wear two hats. So today you're wearing a hat of actually a teacher, because that's who you are, but you're also wearing a hat of a learner, and you're experiencing meeting some ideas for the first time in the way a learner would meet the ideas. So you've got your learner's hat on, and also we're asking you to switch backwards and forwards, which is really rather an odd thing to be asking you to do, between thinking like a learner and thinking like a teacher. And here at the moment, we're talking about a lesson for 11 to 16-year-olds. So that's why we're repeating some of these slides, and we're imagining this lesson now for 11 to 16-year-olds. And here again, we talked about it when we were talking about the lesson for primary, but now we're talking about it for these teenagers, and they're going to stand in the circle and perhaps use a ball of string and perhaps count the number of chords across the circle. And here they've got 8 people, and they have got to be, what they're trying to find out is how many handshakes. So they've done it with 5, and now they've moved on. And this is your 11 to 16-year-olds. They're now thinking about the problem for 8 people. Some of you are teaching at college level, and you're very much on top of all this mathematics. So this is a challenge for you. At university level, so students who go on to university to read mathematics at university, they will be introduced to a subject called graph theory. Now, this is nothing to do, it's nothing to do with the sort of graphs you teach in school. It's a whole theory of, if you like, networks, where you've got points and you've got lines joining the points. So today we've been talking about networks. And you're very you can imagine a network with the internet, with millions of us joined to other people, not necessarily to everybody else. Well, we don't make use of all those connections. So graph theory is a subject. I mean, there's all sorts of subjects in higher mathematics, like topology, which we just sort of dabble a little bit at school, but we don't really do it. Calculus, which in some countries they hardly do any at all. They just do a little bit of dabbling in it. But when they get onto university, it's a big important subject, which it actually gets to be called something else, not calculus. It gets to be called analysis. Okay, that was a diversion.
This is an activity that you can do. Can you do this with one string.
But it's quite a challenge to do it. So it is one of these questions in graph theory or network theory that is a classic question. Can you visit every point with a single continuous line without retracing your steps anywhere? And the very famous problem, which some of you may have heard about, is the Kerlingsberg bridge problem. I know you've seen it before, but please be thinking, this is our lesson for 11 to 16-year-olds. We would get them to do this worksheet and we'd ask the key questions. What we're doing is we're thinking about sequences. So we're now in a secondary school lesson and we're actually trying to help the children. This is pre-algebra. We're trying to help them to understand the rule which takes you to the 100th term of the sequence, or the nth term for a general n. And by the time you've got the nth term, then you're looking for a formula for that term, and now you're in algebra. So this is now, depending on the age and stage of your learners, and this is what you're doing in secondary school, you're looking for the algebra, whereas in primary school, you wouldn't reject a child explaining it with algebra, but you'd be happy to hear that, but actually you'd be happy to stay with numbers too. Now, here again, this is lower secondary. Here we're actually asking the learners to describe the general rules in their own words or in algebraic language. So as they get a bit older, we're wanting them to do it in algebra, in algebraic language with a formula. And here again, we've got the competencies, which don't just apply in maths classroom, but the maths classroom is a wonderful place for developing these generic competencies. And it's so important in this 21st century because computers can do all those things automatically. They can always get right answers quickly, but the routine methods, but people can be creative, they can be innovative, they can apply the knowledge and skills in different ways, and of course, communicate ideas to other people, and that's very important. So we're going to move up to this college level now, 16 plus, and think about what's the difference now, because now we're importantly thinking of the young people who are approaching school leaving, and what is it now that we're going to be doing that we didn't do with the younger children.
You can see what's happening between T3 and T4. You're adding the 4 and then what's happening between T5 and T6, what's been added, then you can develop a generalization which enables you to answer a question instead of actually drawing a triangle that's got 100 levels. You can work it out by working out what the sequence is, by working out what the generalization is. And this is a really nice exercise to learn the concept of creating generalization.
Notice now we're introducing some notation. We're writing down the capital T and we're using it for the triangle number, and we're writing it with a subscript which tells you where you are in the sequence, how far along the sequence you've gone. And now, clever Carl. Now, this is a story about a clever little boy called Carl. It's a true story. And he was about 10 years old, and the teacher thought, well, now I'll give them something to do, and this will give me a bit of a rest because it will take them a while to add up the numbers from 1 to 100. And in about 2 minutes, Carl had got the answer, and the teacher could hardly believe it. So what had Carl done? Well, what he'd done is, in his mind probably, he didn't write them all down. He'd written 1 plus 2 plus 3 plus 4 plus 5. He'd thought about that. And then he'd thought about taking them in the opposite order, 100, 99, 98, 97, 96, down to 1. And he'd realized is if you did it that way, that 1 added to 100 gives you 101, 2 added to 99 gives you 101, and you can go on and on doing that. And that would tell you that this question that the teacher had asked, what's the sum of the numbers 1 to 100? He'd say, oh, well, it's just 100 times 101, and you halve it. Okay, because you've written both things twice, and that's 5,050. And so he gave the teacher the answer, and he had worked it out, but then he became when he grew up, he became a very famous mathematician, and it was Carl Friedrich Gauss. He lived in the 18th century, and he's commemorated on a German stamp there, and there's a German banknote with his slightly older Gauss on it. He was a very, very, he did lots and lots of mathematics. And this is something that's a different theorem about triangles and triangular numbers. It's nothing to do with what we've been doing so far. But his Eureka Theorem, it's called, Gauss's Eureka Theorem, was that every number, every whole number, can be written as the sum of 1 or 2 or 3 triangle numbers. You don't need more. So any number at all, you can write it as the sum of 3 triangle numbers, but some of them you can write as 2 triangle numbers, and the triangle numbers themselves, it's just 1. So that's the Eureka Theorem. It's quite hard to prove, but it's a lovely idea. It's easy to explain. It's hard to prove.
Really think about that, because it blew my mind when I realized it, that every number can be written as a sum of 1, 2, or 3 triangular numbers. Every number.
You can try it for yourself.
Yeah, yeah, have a go.
But if it's a big number, if it's a big number, it'll be difficult perhaps to find the right 3 to add up. Okay, but it is possible, and it's in itself, it's quite a nice investigation. Proving it's quite difficult, but let's come back to what you might do with your class of students. So you might give them the same table with lots of gaps to fill in. Okay, it's pretty obvious then how to fill in the gaps, and then you can ask them what they notice about the table. You could tell them the story and discuss the method. So this is how you could use this story in teaching your 16-year-olds. What key questions would you ask your students about this? We're giving you some key questions, but we also expect you to be thinking them up for yourself as a teacher.
Well, what do you notice? We've looked at these triangles. You put 2 triangles together, kind of back to back, and they make a rectangle. If you've got 2 T5s, your rectangle is 5 by 6, which is 30. So 1 T5 is 15. Oh my goodness. Could it be that simple to work out what it is? So the same way, if you put 2 T100s together, you then have 100 by 101, because they're just offset by 1. So 1 T100 is half of 10,100, which is 5,050. Easy peasy, lemon squeezy. And and you can see the numbers using the clever Carl's system. T7, you can do 1, 2, 3, 4, 5, 6, 7 plus 7, 6, 5, 4, 3, 2, 1. 2 T7s is 8 plus 8 plus 8 plus 8 plus 8, which is what it is? 7 8s. So T7 is half of 7 8s, and it boggles my mind. And this is a great way as well, guess what, to work with times tables. When you're doing wonderful things like this, you're working with your times tables and at the same time having your mind blown by what numbers do.
So we are talking about 16, 17, 18-year-olds, and they need to know this formula and use it, but they also need to know how it's proved. Okay, and it's really important that they don't just use formulae, but they can actually prove them. So what about the proof here? Now, we've laid the groundwork. If you're teaching this lesson, you will have laid the groundwork for this proof. So the sum of n terms is the first term. and then a plus d is the second term. It's the first term plus the difference. And then the next one, the third term, is a plus 2d, and so you go on. And the nth term is a plus n minus 1d. And then if you write the terms in the reverse order, like you just saw for T7, there they are. And then if you add the pairs of terms, just as we did for T7, each time, now look, each time you've got 2a, and you've got n minus 1 times d, and you've got that n times. So twice the sum we're looking for is n times 2a plus n minus 1 times d. And then we divide by 2, and there's your formula. Now, it's not something I would suggest that you show the children, no, not children, are they? The young adults now, that you show these young people and explain it to them and then expect them to learn the proof. That's not the way to teach. One thing that we often do is do what we call a proof sorting, okay? So let's go back to we'll mention the previous slide and the clever Carl method. What was it leading up to? It was leading up to this. So now what I would do is I would cut this, what you see on this page, into strips. I would cut this into about 8 different strips, and then I would shuffle them all up, and I would give a group of probably, well, a pair of learners or 3 or 4 learners, I would give them the strips, and I would say, now, you've got to make this into a proof. This is all in a jumbled up order. Can you sort the proof, and can you get it in the right order? Okay, and so you're not writing it on the board and expecting them to listen to you and just and follow what you're saying. You're giving them something to do and to think about and to talk to another student about. It's actually a pretty good thing just to do in pairs. Okay, and so you don't show them this proof, and in fact, I would suggest that you don't actually use this proof. Sorry, use this formula. You actually lead up to it with the clever Carl method, with numbers, and then you give them the proof sorter, and then you discuss it as a class. You ask some learners, some students to come up to the board and explain it to the rest of the class. And when everybody in the class has sort of thought about it a lot, and almost everybody has understood it, then's the time to use it. So you don't use formulae, as you can possibly avoid it, that you haven't been able to, the children haven't been able to, the young adults haven't been able to understand.
Fascinating numbers. You've got two triangle numbers. One is T6, the yellow one's T6, the blue one's T7. What does T6 plus T7 make? You put them together in that way, you have a square. So 2 triangle numbers added together, actually 2 sequential triangle numbers added together make a square number. And that is another wonderful fascination.
This happens for T6 and T7. Does it happen for all the triangle numbers? When you add a triangle number to the next one, does it always give you a square? This is a generalization, and we'll leave that with you, but it's a nice question, I think. What we're going on to look at is, again, the same thing, but now for the older children, what they're doing is looking at the sequence of triangle numbers, and they're looking at the sums of 1 to n each time, and they're recording the answer to each of these calculations and then leading on to doing it algebraically. So here we have now what we would do with these young adults at the college level, which is just an extra layer above what we would have done with the 11 to 16-year-olds. Although some 11 to 16-year-olds could perfectly well get this far. The Mystic Roses again. So we've got here the 15-point and 16-point Mystic Rose, And for the 15-point mystic rose, we have got the calculation, which is a half 15 times 14 to give you the number of chords, but divide that's a half, which gives you 105 chords in the mystic rose, or handshakes, which is then if we look at what we get for the other one with an even number, here it's the same way of working it out, but now we've got 120 handshakes. And look what we add to T15 to get T16. From 105 to 120, we add 15. So to T15, to Tn, we add n to get Tn plus 1 in general. And this is the sort of pattern that we're evolving.
And going with these larger numbers helps it gel, helps the learner to actually see how it works. Rather than you keeping the smaller numbers, it might not work, but then you go to the bigger numbers, oh, it still works. And it aids their credibility and their buy-in to it.
Now, for these young adults, we're giving an inductive definition of the sum of the series in terms of going from one term to the next in a sequence, and we're giving a formula which expresses it without this induction, this transition from one term in the sequence to the next, and it's a half n times n minus 1. That's the sum of your sequence, your series, when you've got first term is 1 and common difference is 1.
And you can really see it beautifully depicted there.
Yes, and now what would have been our learning objectives for these senior pupils preparing for their school leaving exam? We would expect them to investigate number patterns leading to arithmetic sequences and summing series. We'd expect them to understand, not just investigate, but understand the sequence and the algebraic representations and summing to n terms of the series. And we'd also expect them to prove the results, the formulae. We would want them also to have developed by now pretty good visualization skills, because what I find is professional mathematicians who do research level mathematics often communicate with each other by drawing pictures. And the pictures, that's not the mathematics, but that is actually, well, it is the maths, but in order to write their research paper, they put it all in terms of formulae and words. But when they're actually informally interacting with another mathematician, they often are visualizing something which they can do in a diagram or a chart or a picture. Visualization.
And they make 3D gadgets as well, 3D models as well.
Yes, and visualization is hugely, hugely important in mathematics. And problem-solving skills in maths and in all sorts of ways. Mathematicians are very, very employable. In my country, in the UK, they get the highest starting salaries of any graduates. The mathematicians do, because they're good at solving problems. And so much of what those problems involve might be statistics, but it involves some sort of mathematical thinking or mathematics. And so these generic competencies, which our young school leavers would we hope have, which is being able to think creatively and reason logically. The maths classroom is the perfect place for developing these reasoning powers, which they can apply to many problems that are not basic in mathematics. They can apply knowledge and skills, solve and interpret problems, and develop communication skills. That's what we want to do. Those are the really useful skills that we want you to make sure, we want to help you, to empower you, to make sure that all your learners have acquired in good measure by the time they leave school. There are 3 of these activities on the Aiming High website.
These activities themselves you can just use in your classroom. They've got the key questions, they've got all the different activities, they've got the worksheets, everything is in here.
We're having greetings here on the chat from Gary and from Mary in Kenya. Yes, I remember Mary. We've met before.
Yes.
Oh, she's come up. Yes.
Well, I'm going to let you into a secret.
Eric and
It's not a
Tanzania
big
as well.
secret. Mary actually did exactly what we've just been talking about, didn't you, Mary? From Kenya.
Yes, I did. Yes, I did. But it's still so refreshing to just sit here and, see this afresh. Yeah, I did.
I think it was about 12 years ago that Mary wrote to us from Kenya and said she wanted to come on one of our courses. We welcomed her, and she did the 14-week course, and then she did a 2-year course, and then she went and did a PhD, and now she's a university lecturer. But when we first met her, you were a school teacher, weren't you, Mary?
Yes, I was. Yes, I was in a high school.
Yes.
Thank you. Even now, I just appreciate the progression, having sat through the 2 hours and just using the same, just building up the idea. I just appreciate that. Yeah. For the different levels. Yeah.
Thank you, Mary. We started this idea because of COVID, and we thought of all these children at home, and the household where they had children of different age groups. So how could we best help them? And so we decided to do what we call an inclusion and home learning guide, where in the one document we take the family, the adult who's got to cope with this situation, from starting with an activity that everybody can do together, and then separate activities for the different age groups, but all on the same theme. So we're going to stop there and say goodbye because time is up.
Bye, everyone.
Thank you, everyone.
Bye.
Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye, everyone.
Goodbye.
Bye-bye.
Here's the mic.
Thank you for joining us. Bye-bye.
The Global Teacher Empowerment Network's mission is to empower teachers to improve education in disadvantaged communities, to give children better opportunities in life. GTEN introduces new skills for the teaching of mathematics and provides learning resources and professional development workshops.